Hi, and welcome back to LigerLearn. In this video, we will begin looking at the Haskell programming language, covering a range of topics that you need to know as a beginner. Let's get going. We'll cover quite a lot of the basics in this module, and by the end of it, you should have a decent understanding of the Haskell language's rudimentary syntax and structure. We begin by discussing what Haskell actually is, and quickly move on to looking at types, functions, and conditional if-then-else expressions. Many of the things discussed in this module are focused on giving you, the beginner, a good understanding of general concepts such as whitespace and comments in Haskell, as well as providing a discussion of ideas such as side effects and purity. By the end of the module, you will also have seen some very simple examples of recursion and importing, preparing you for the next steps in your learning journey. Let's crack on. So, what is Haskell? Well, the dictionary definition is that Haskell is a general-purpose, statically typed, purely functional language with type inference and lazy evaluation, named after the logician Haskell Curry. That's a lot of words. It's a bit of a mouthful. Let's go through each bit one by one and make sure you understand. General purpose. This means it can be used in a general sense for a wide variety of domains. This is in contrast to a domain-specific language, which would only be used for a specific domain. Statically typed. This means that the type of values are known and checked against at compile time. This is in contrast to dynamic typing, where the type is verified at runtime instead of compile time. Purely functional language. Purely functional refers to Haskell's programming paradigm. In this paradigm, immutability is the default, and if you call a function with the same arguments, it will always return the same result. As everything is immutable, functions are said to have no side effects. We'll explore what being pure means and how it relates to side effects in one of the next slides. With type inference. This refers to the fact that the programmer does not always have to declare the types of variables and functions in the code. The compiler is smart enough that it can usually figure it out for us. We will see this in action in later places in the course. Lazy evaluation. This means that only that which is needed to compute the value is actually computed, and nothing more. We touched on lazy evaluation briefly in the previous section on the lambda calculus, and we will see it again in action later. Unlike other programming languages such as C and Java, which have their origins in industry, Haskell's origins are from academia. In the 1980s, there were a number of functional programming languages, with the most widely used being a language called Miranda. Miranda was proprietary software, and so in 1987, at a conference on functional programming languages and computer architecture, it was agreed that a committee be formed to define an open standard for a functional language. The point of the committee was to consolidate the existing functional languages into a common one to serve as a basis for future research. This eventually resulted in the first version of Haskell being defined in 1990. Over time, research continued and a number of features kept being added to the language, eventually resulting in newer versions. The most important milestones are the publishing of the Haskell 98 language standard and the Haskell 2010 language standard. The de facto compiler of the Haskell language is the Glasgow Haskell compiler, commonly abbreviated as GHC, and is what we will be using for this course. The compiler is what takes the code you write and compiles it down to machine instructions so that the code can then run. If you would like to learn more about the history of the Haskell programming language, then check out the paper available at this link. Let's begin by talking about Haskell's Prelude module. The Prelude is a Haskell module which gets imported into each Haskell file by default. The module contains a whole bunch of inbuilt types and inbuilt functions, which you then have access to within your Haskell file. You can then go ahead and use the types and functions without having to worry about importing anything. It is customary for the first program you write in a language to be the Hello World program, and so we are going to follow that custom too. To that end, we will be using GHCI. GHCI is a read eval print loop, or REPL for short. It will read and evaluate the expressions we provide to it and then loop back to reading and evaluating again. The image here shows an interactive GHCI session where we run our first program, the Hello World program, Let's go through each step in the session together. First, we run the ghci command to open ghci. If you are having problems doing this, refer back to the previous module where I showed you how to install Haskell and get the ghci prompt working. You will notice that the prompt begins with Prelude. In a version of ghci which came out after the one I am using here, the prompt changed and instead displays the string ghci. Either way, the prompt is not that important. It can actually be customized to whatever you would like it to show anyway, so don't worry if it's different to what I'm showing here. Next, we call the putString and newLine function, which is named putstrln for short, with the hello world string passed to it as an argument. We can see that the expression is evaluated by ghci and it prints hello world on the screen. If you're asking yourself, why do we need to put a new line at the end of the string, which is what the ln bit of the function name represents, then check out the next line in the ghci session. There is also a function called putString in the Prelude, which I have called here with the exact same hello world string argument. This works just like the other function, but does not put a new line at the end. And as you can see, the results of doing that mean the prompt is placed at the end of the line instead of on a new one. We want to avoid that, and so we usually use the putString and newLine function as the default. The final command we give in the session is :q, which stands for quit, which leaves the ghci session. That's it, your very first ghci session and the simple hello world program. In the next sections, if we are referring to types and functions without an explicit import and you wonder where they are coming from, then remember they are most likely coming from the Prelude, which, like I said before, is automatically imported and available to us. The Prelude module is not without controversy though. Many people believe it provides an antiquated way of doing things and should be replaced. People dislike the Prelude so much that they have even gone ahead and defined their own versions to replace the default one. Don't worry about that and the controversy. For us, we want to learn functional programming, and the default Prelude is good enough for that. So that's why we will happily be using it throughout the course. We mentioned before that Haskell is a pure language where everything is immutable by default and there are no side effects. But what exactly does that even mean? Consider the following Python code. Now don't worry if you don't understand Python. This example is simple enough that I'll be able to explain it to you from scratch. We define a variable named a to be equal to 0. And we define a function called addA to arg. This function refers to the global variable a, so we declare a as referring to the global within the function body. We then change the value of a, assigning it the value of a plus 1. This means change the value of a to be whatever a is now equal to plus 1. Then we return a plus the argument passed in, whatever that is. Now we call the function twice, with the same exact argument 5. The first time the function is called, it will return 6, and the second time it is called, it will return 7. This is what is known as an impure function, because each time it is called with the same argument, it returns a different value. Another thing which is commonly said regarding functional programming languages is that there are no side effects. What exactly does side effect mean? Side effects refer to the mutation of some state as a result of calling a function. So, for example, in the case of our function, every time it is called, the variable a is mutated and the value is changed. Here, you can see that as a side effect of calling the function, the variable a is mutated. So the first time the function is called, as a side effect, the value of a is set to 1. And the second time it is called, as a side effect, the value is set to 2. In contrast, a pure function will always return the same value when called with the same arguments. This is because values in pure functional languages are immutable. This means they cannot be changed once set, so there are no side effects. Now technically, Haskell has ways in which you can refer to and mutate global state, but that is an advanced topic and is kind of a last resort, and so we will not be covering it in this beginner's course. Sometimes you may also hear the term referentially transparent being used to describe a pure function. This means the same thing, that given the same inputs, the function would always return the same output. Now what does purity or referential transparency give us? Well, firstly, it makes reasoning easier. Functions are treated like mathematical objects, and so they are well suited to formal reasoning. You also don't have to worry about some shared mutable state, which could be referenced anywhere within your program, since everything is immutable. Secondly, parallelism becomes easier. With the guarantee that expressions are not going to affect one another, evaluating in parallel becomes much simpler. Let's now move on to the practical side of things and learn how to actually code in Haskell. In Haskell, we use the equals sign to bind an identifier to an expression. An identifier is just a name, and every binding has a type signature, which we can declare using the double colon symbol. So for example, in this code, we declare an identifier named x is of type integer. An integer is any whole number like 1, 2, 3, etc. And then we bind the integer value 1 to the identifier x. Once you have bound a value to an identifier, it is immutable. This means you cannot rebind the identifier to a new expression or value. If you try to do that, you will get a compilation error complaining that there are multiple declarations for the identifier. In this case, you can see that trying to set the value of x to 5 once it has already been set to 1 means we get this error. This error is quite helpful. It says that in the file scratch.hs, which is the file in which I was coding, on the 7th line and the first column, the error of multiple declarations of x was raised. Then the compiler helps us by telling us the two locations in the file where x is declared, line 3, column 1, and line 7, column 1. We could use this information if we wanted to fix the error and set the value to a variable with a different name. For example, setting y to 5 will work because there is no conflicting variable name. Even though identifiers are immutable, you will still hear people calling them variables. This is partly because conventionally that's what we call them, and also because, as you will see later when we look at functions, function arguments will vary when we apply them. Don't be confused, everything is immutable, even though everyone calls them variables. You will get used to it. Now you will notice that for the binding of y, we did not declare the type. This is because, as we mentioned before, Haskell has type inference, so the majority of the time, if we do not declare the type, the compiler can infer it for us. Even though you don't strictly need to declare types, it is recommended that you do for all top-level declarations within a file. If you load the file in GHCI, you can use the command :type followed by the variable name, which in our case is y, to see the type which the compiler has inferred. In our case, it is obviously an integer. And as a shorthand, you can also just type :t followed by the variable name. There are a number of inbuilt types in Haskell which you should definitely be aware of. The first type is bool. The bool type refers to a Boolean value. In other words, a value which is either true or false. In this code example, we declare two variables, a and b, which are both of type bool. Note the shorthand of declaring variables with the same type using a comma, then the double colon, and then the type name. This is just for convenience to avoid having to repeat yourself and define each variable on its own line. As we can see, the variables a and b are bound to the values true and false respectively. The next type is char. Char is short for character, and a char value represents a Unicode character. Some people pronounce char as car. Either way is fine. In this code example, we declare four variables, d, e, f, and g, to be of type char. Then we bind each of these variables to a different Unicode character. When binding a character to a variable in Haskell, we have to surround it by single quotes, as is done here. This is important. If you use double quotes, you will get an error. Now I've purposefully used characters from different scripts here to illustrate that Haskell understands Unicode, which is the standard for encoding text in different writing systems. The value of the variable d is from the Latin script, e is from the Devanagari script, which is used for some Indian languages, f is from Cyrillic, which is used for Russian and other languages in Central Asia, and g is a character from Mandarin, which is used in China. If we try to show the values in GHCI, you can see what will be output. Only the value h is displayed properly, and for the others, we get these strange numbers. This is normal. These numbers are the Unicode code points representing the character. GHCI intentionally shows these characters like so, because it does not know whether the command prompt being used can handle the Unicode character. It is better to see these Unicode code points so that you understand that it is a Unicode character than a weird box which tells you nothing, which is what would appear if the terminal didn't understand Unicode. The next two types are int and integer. Let's look at int first. An int is a signed integer with fixed precision. Signed means that the number can have either a positive or negative sign attached to it. This is in contrast to an unsigned int, which has no sign and so can only be positive. Fixed precision means that the value can only be between a specific interval. The actual interval depends on your computer architecture, but the Haskell standard states that an int must be at least 29 bits, so you are guaranteed to have at least 29 bits of fixed precision, but this will vary depending on your machine. You can see the range of values allowed for an int on your computer by referring to the inbuilt max bound and min bound constants. We define the biggest int and smallest int to refer to these constants in our code. And here you can see what these values are by calling them in the GHCI prompt. The biggest int is a huge positive number and the smallest int is a tiny negative number. You can see that for all intents and purposes, int will be sufficient to contain all of the integer values we will probably ever need. The other type is integer. The integer type represents a signed integer with arbitrary precision. Unlike int, which has fixed precision, an integer has arbitrary precision and so is only limited to the memory of your machine. So it can represent both positive and negative numbers, which are far larger and smaller than could be stored in a normal int. In this code example, I've created two variables of type integer called even bigger int and even smaller int. Then I have bound these variables to values which are even bigger than what we saw for the max bound and even smaller than what we saw for the min bound for an int. These are perfectly valid values for an integer, but not for an int. The majority of the time we will just use a plain int because it is sufficient. Another thing to note here is the usage of what is known as camel case to name variables, where apart from the first word, each word which is placed together in the variable name has its first letter capitalized. This is the convention in Haskell. The next type is double. A double is an IEEE double precision floating point number. In other words, a double is a generic way of representing numbers with a decimal point. But remember, a double value has only 64 bits and so not all decimals are fully representable. There is another type called float, but that has only 32 bits to represent decimals and so it is not really used, so we will ignore it and prefer double. The next type to consider is a special kind of type, that is, lists. We can declare a list containing items of a specific type and populate that list with a special convenient syntax. We refer to a list using square brackets. For example, the variables j1 and j2 here are both of type list of int. Then we can bind the variable to a value using the special list syntax, which is quite simple. We place the values we want in between the square brackets separated with a comma between each value. So in this case, for j1, we bind the list containing the values 1, 2, 3, 4 and 5, and for j2, we bind the list containing the values 6, 7, 8, 9 and 10. Likewise, you could declare a list of any type, a list of double or a list of bool or whatever, and populate it using this syntax. Lists are really important, and we will look at them in more depth in a later module. For now, we are only covering the basics of lists so we can understand another important type, and that type is string. In Haskell, by default, a string is just a shorthand for a list of characters. I've defined three different values here, k, l and m, which we will see are all equal. The first is k, which is defined as having the type of list of char and has the value of a list containing the characters h, e, l, l, o. The next is l, which is defined as having the type of list of char, but we bind the value using this new syntax. Here we place each of the characters next to each other within double quotes. And the last one is m, which is defined as having the type string, and we use the double quotes to bind the same value of hello. As I said before, each of these is the same. The string type is a convenience type representing a list of characters, and rather than having to create a list each time, like we do here with k, we can use double quotes to just create the string directly, like we do with m. We can see that they are equal by inspecting the GHCI output for each variable and seeing that they all output the same thing. Before we move on to the next type, I want to briefly mention a useful operator when it comes to lists, and that is the concatenation operator, denoted by two plus signs together. What this does is join two lists together and produces a new third list. For example, here with the variable j1 and j2, I am concatenating the two lists together. Since the two lists j1 and j2 are of type list of int, then the concatenation is also a list of int. We can see that it results in the two lists being put together like so. Another example would be if we put K and L together. Since K and L are both lists of char, then the result of their concatenation is also a list of char. But remember that we can just call a list of char a string for shorthand, and so that is what we have done here. And concatenating the two strings K and L gives us the string which is just K and L put together. We'll be using the concatenation operator for some of our examples later in this module. The last type I want to cover has another special syntax in Haskell, that is, the type of a tuple. A tuple is a finite sequence of elements. This means, unlike a list, which can have any size, and even potentially be infinite, a tuple always has a fixed size. Also, unlike a list, which can only contain values of a single type, each value of a tuple can be of any type. Let's look at some example code. Here, we are declaring a tuple with two elements, with the first element being an int and the second being a double. Since there are two items in the tuple, we call it a two-tuple or a pair. Now let's consider this tuple. There are three items in the tuple, so we call it a three-tuple or a triplet. The first item is a string, the second is an int, and the third is a character. You can see the syntax for tuples is quite simple. In the type signature, the tuple is defined by placing a comma-separated list of the types of the tuple's elements within brackets. Then you provide a binding of values for the tuple by doing the same thing, but replacing the types with values. What is the biggest number of elements you can have in a tuple? Well, according to the Haskell standard, every implementation must support tuples with up to 15 elements, so we can happily create anything up to a 15 tuple if we need to. There is a special type of tuple, the zero tuple, which is called unit in Haskell, or sometimes the empty tuple. There is only one valid value for a tuple of type unit, and that is the empty tuple itself, represented in the same way the type is, as an empty pair of brackets. If you are familiar with other programming languages, you can think of it kind of like the type void in C or Java. This type is not important for beginners. It will become important as you start to understand intermediate and advanced concepts. I'm just mentioning it here so that you are aware it exists. A word of caution on tuples. In Haskell, it is not considered good practice to use tuples which are large in size. Occasionally, using a pair or a triplet is fine, but anything other than that should probably be avoided. This is because Haskell gives you better options for modeling your types, which can be used instead. We'll cover these in later sections. There are a number of built-in types in Haskell which I have not covered, but I've covered the most important built-in types here, and we will build upon this foundational knowledge throughout the course. One of the things to make sure you know as a beginner of Haskell is that whitespace in your source code definitely matters. For those of you coming from a language like Python, where whitespace also matters, this won't be a big deal. But for those of you coming from a language like C or Java, where whitespace does not matter so much, this can come as a slight shock. Consider the following code. We have the type signature of a variable a on one line, and then we try to bind a value to a on another line, but this second line has a bit of whitespace before it. If you try to compile this, then it will fail with an error. The error says, illegal type signature int a. Type signatures are only allowed in patterns with scope type variables. This error message is completely incomprehensible. Now if you fix the code so that there is no whitespace difference between the starting points of the lines, then everything works fine. You would never guess from this error that the actual problem is a whitespace mismatch. Sometimes you get a better error like this one, which says parse error, and you can more easily identify whitespace issues. When it comes to whitespace in Haskell, there are some rules you need to know, but we are just starting to learn the language, so I can't really explain them to you completely yet. It is kind of like the chicken and egg problem. I need to tell you some rules about Haskell code, but first I need to tell you how to code in Haskell. But for now, if you're getting errors which you cannot understand, then try to see if something went wrong with the whitespace in your code. Some whitespace guidelines that you should follow. Always use spaces, do not use tabs in your code. This makes things simpler. Also, make sure you are writing code exactly as it is shown in the code snippets on the slides, even considering the whitespace. Try to make sure that each line begins at exactly the same point for now. This is a good general guideline for beginners, but as you will see later, certain constructs require you to indent your code. As we work through the course, I'll keep you updated on whitespace concerns so you know how it affects the code you write. The rules for whitespace are actually quite intuitive, so you will find yourself appreciating them as time goes on. Don't be too scared about it for now, just follow the guidelines I've said, and you should be fine. Why do we even bother declaring types? In the simplest sense, the purpose of having types is to constrain the value of a variable to a valid set. The process of verifying and enforcing the type constraint, expressed in your program, occurs at compilation time and is known as type checking. So for example, if we declare a variable, a, which is of type integer, and then we bind a to the character 5, we will get an error. We can see from the error it is a type mismatch. The compiler expected an integer but got the actual type of char. The program will not even compile until this problem is fixed. By having the compiler perform type checking, we ensure our program is type safe, which removes the chance of a whole class of type errors from potentially occurring. Expressions which type check are said to be well formed or well typed. Haskell has a stereotype of being difficult for beginners. Part of this difficulty comes from the experience of beginners in the language always facing issues with the compiler throwing type errors. One of the reasons for this is because compared to other languages, Haskell is more strongly typed. Certain types of code, which is permissible in other languages such as using what's known as casts or implicit type conversions, is not allowed in Haskell. As a beginner, it may seem annoying to you that you are always coming across these errors, but after a while you will come to value the fact that the compiler doing this leads to stronger guarantees of the correctness of your code when it runs, and so in the long run it is worth it. Don't fear or get angry at error messages as a beginner. Try to understand them so they become easier to deal with in the future, and be glad that the error is being caught at compile time and not at runtime. There are two types of comments in Haskell. The first is line comments. Line comments start with 2 consecutive dashes. Any text after the double dashes up to the end of the line count as a comment and will be ignored by the compiler. The second type is known as nested comments, or sometimes block comments. These comments start with an open curly brace and dash, and end with a dash and close curly brace. Any text within the comment will be ignored by the compiler. Sometimes certain additional markings after the start of a comment indicate a comment with a specific purpose. For example, a special type of block comment is known as a compiler pragma. These are additional hints given to the compiler. You can see here that the pragma is contained within a special type of nested comment where we add a hash symbol to the open and close of the comment. This particular pragma indicates that we want the compiler to treat this file as per the Haskell 2010 language standard and not any other one. Some pragmas must be placed in a specific place in the file. For example, language pragmas, like the one we have here, must be placed at the top of the file before any code. Other pragmas may not have this restriction and can be placed in different places within the file. Another type of comment you will see is used for documentation purposes. In this case, after a double dash, there is a space and then a pipe, after which there is a description. This type of comment is intended to be used by documentation generation tools as the main text to describe the function. Don't worry if you don't understand the function definition syntax of Square here. We haven't covered defining functions yet. I'm just showing this example to you so you can see the comment style. There are some other comment styles you can use for documentation too. You can see them if you follow the link shown here. And that's it for comments right now. We will mostly just be using line comments and sometimes block comments in the course, but I've covered the other types just for completeness. There are 2 types of file endings which are conventionally used to represent Haskell source files. The first one is the main one, that is .hs. This contains code and comments just as you would expect and as you have seen in the previous examples. The second one is .lhs, which stands for Literate Haskell. This format is different and inverts the relationship between code and comments. The literate style is inspired by Donald Knuth's literate programming paradigm, in which he encouraged comments by making them the default. Let's look at a literate Haskell example. In a literate Haskell file, comments are the default, and if you want to write code, then you need to start a line with a greater than symbol, as you can see here. The literate Haskell style rarely gets used in actual program code, but for tutorials and short code snippets, you will find it used to be quite common, and so it's important to at least be aware it exists in case you come across it or any files which end in .lhs. Let's now look at how we can define some simple functions in Haskell. Just like simple values, functions themselves all have type signatures. Type signatures for functions follow the template I've placed here. First comes the function name, then comes the double colon, then comes the type of the first parameter to the function, then a dash and a greater than sign, which is supposed to represent an arrow, then the type of the next parameter, and that repeats until you have specified the types of each of the parameters to the function. You then end with another arrow and type, with this final type representing the return type of the function. Every function has at least one binding. Later on in the course, when we come to pattern matching, we will see functions which have multiple bindings, but for now, all our examples are simple and will have only one binding. Take a look at the template for a binding which I've placed here. For each parameter type, which is declared in the type signature, there needs to be a parameter name given in the binding. The parameter names come after the function name and are only separated by a single space being between them. This is known as juxtaposition. Let's now take a look at an actual example. There are two parts to the function definition here. The first, at the top, is the type signature, and the second, underneath it, is the binding. According to the type signature, the function takes two ints and returns an int. So we know there are two parameters to the function which we need to name. In the binding, we have the function name and the names we want to give to the parameters, all separated by a space. The names could be anything, but I've just given the names A and B for simplicity. Then the logic in the binding simply uses the inbuilt plus function to add the variables A and B together. Now let's look at actually calling the function. You can see here that the function is called by placing the values we want for the parameters next to each other. So for the first call, A becomes 202 and B becomes 6 to give us the value 208. And for the second call, A becomes 89 and B becomes 32 to give us the value 121. So for those who are learning Haskell after learning another programming language, like C or Java, there are a few things to note here which may seem a bit weird to you. First, the type signature gets its own line. In those other languages, usually the type is placed next to the parameter and the return type is placed before the function name. This style is different, but not difficult. Now you have been told how to read the type signature, at least for the simple case, it should all make sense. Second, there are no brackets in the binding, or when we call the function. In other languages, to call a function, you need to place the arguments to a function in a comma-separated list with brackets. This is not needed in Haskell. In Haskell, the only time you need brackets is if you want to group an expression to help remove any ambiguity, not for actual function application. This style of placing the variables next to each other, separated only by a space, is quite common in functional languages, and as I've already said, is known as juxtaposition. Let's take a look at another example. If we look at the type signature first, from the type signature we can see that the function is named add3doubles and takes three parameters, which are all of type double. It returns a double as well. From this we know that the function binding should have three variables declared. So if we look at the binding, we confirm that this is true. There is the function name, then three variable names for the parameters next to each other, separated by a space between them. Then there is the function body, which just sums all of the function parameters. And you can see here that we call the function in the same way, passing each argument with the space in between. A quick note on brackets, they are only needed when you need to perform grouping in a compound expression, or to remove ambiguity. So for example, here we are calling the function add2ints and passing the first parameter of 50. However, the second parameter we want to pass in is the result of calling add2ints again. And so we group that call to add2ints in brackets, so there is no confusion. If we did not provide the brackets, the compiler would throw an error because it would think you are applying the function to 4 arguments instead of 2. Another note on unused parameters in functions. In the case where a function takes a parameter, but the parameter is not used in the function body, we can replace the name with an underscore. So in this case, we have a function which, when given a 3 tuple, will always return the first element in the tuple. There is no need to provide parameter names for the other elements in the tuple, and so we just use an underscore instead. In certain cases, this can increase clarity and understanding because by immediately looking at the function, you understand that the parameters are intentionally unused. You call the function like normal, as you can see here. There is a lot to cover on functions, and we will look at them more closely in later sections, covering topics such as partial application and currying, but for now I've given you just enough information to understand the basics. Let's quickly go through a number of built-in arithmetic functions in Haskell, which you would expect any programming language to support. You can use addition, subtraction, and multiplication as you would expect, and as we have seen in previous code examples. In these examples, we are operating on two ints and returning an int, and so the type signature of int is satisfied. Now let's look at division. Consider this simple example where we declare d to be an int equal to 20 divided by 2. Now in our head, we know it should equal a whole number, 10. This will fail to compile with an error message, which you will more than likely not understand at all at this point. Let's take a look at this error message. No instance for fractional int arising from a use of division in the expression 20 divided by 2. What does that even mean? Well, to tell you the truth, you won't be able to truly understand this error until you have understood something known as type classes in Haskell, and we are not going to cover that until later in the course. So for now, I'm sorry, but we won't be able to fully understand this error message. Don't worry though, when we cover type classes, I'll make sure to come back to this example and explain it properly. For now, just understand that when using the slash to perform division, the type needs to be a fractional type. And double, which is a type we know, just happens to be a fractional. An int is not a fractional, and so this does not work. So if we replace the type with a double, everything works fine as we would expect. Let's take a second to pause and understand conceptually what happens when you divide something. In this particular case, we are dividing 20 by 2, which we know by performing the calculation in our head will result in a whole number, 10. And so an int should work here, right? Well, yes, in this specific case, but no for the general case. For this example, we may be able to perform the calculation to see that it should result in an int, but in the general case, there is no way to know that in advance. I mean, if we knew the result of a calculation in advance, then there would be no need to perform that calculation since we already have the result. Division, by definition, creates a fraction, and so by definition, having division return an int in the general case makes no sense. In some other languages, what happens is that some implicit rounding and conversions take place to allow this type of code to compile, but Haskell is strongly typed. Everything needs to pass the type checker, and so any rounding or type conversions need to be explicit. So on the issue of basic arithmetic, you may come across errors like these. Remember, if it says no instance for fractional, try changing the type signature to be a double instead. As a beginner, these errors will be annoying, but once you understand Haskell more, and in particular type classes, you will find it quite useful. But this still does not answer the question for our specific case. In our case, we know 20 divided by 2 is a whole number, and we don't want a double, we definitely want an int. In that case, we can use the div function. The div function will perform the division, then round down to the closest int. Unlike the built-in arithmetic functions, which we can place in between the two arguments, just like we would do in mathematics, for the div function, we can't do that by default. Instead, we pass the two numbers to be divided to the div function, and we do that by putting them next to each other with a space between them, just like for the simple functions we saw before. Another arithmetic function I would like to show you is the negation function. The negation function, or negation operator, is a built-in prefix operator in Haskell, which is just a dash that you put in front of a number to turn it into a negative number. You can see how it is used in the code. Where there is potential confusion over functions or inbuilt operators, it makes sense to put the number as well as the dash in brackets to avoid ambiguity. The final inbuilt arithmetic function I want to show you is exponentiation, which you perform by using the caret symbol. So in this code example, we are raising 2 to the power of 3, which is obviously 8. When it comes to calling a function, so far we have seen two places in which the name of the function can be placed. The first is infix. Infix refers to the fact that the function name sits in the middle of the arguments. We are quite comfortable with them when it comes to arithmetic functions because this is the way in which we learn mathematics at school. So for example, we have seen how plus, minus and multiplication can all be applied by placing them in the middle of the two arguments. Aside from arithmetic functions and Boolean operators, these are quite rare in Haskell. The second is prefix. Prefix functions place the function name before its arguments. These are the most common in Haskell, and the majority of functions we use will be prefix functions. We've seen an example of doing this before by using the built-in div function, which takes two arguments and performs integer division. There is also a third place the function name can be placed, known as postfix. This is when the function name comes after all of its arguments. This is not used in Haskell at all, and so we can just ignore it. I'm just mentioning it for the sake of completeness. A cool feature of Haskell is that you can turn a prefix function into an infix one by surrounding the function name in backticks. Let's take a look at this. You can see here that the div function is placed between backticks, and it is also placed between the two arguments. F and J are equivalent. Which one you should do just comes down to the programming style and your preference. In this case, it might make sense to prefer the infix notation because you can now read the code like you would read division, 20 divided by 2. When the function only has two arguments, it can sometimes make it easier to read like in this case. But when there is more than two arguments, using backticks is rare. Let's take a look at the add three doubles function which we saw before. The function is quite simple, it just takes three doubles and returns the sum. In prefix notation we would call the function like so, nothing special. But with backticks, you have to wrap the invocation with the first two arguments in brackets and then provide the third argument. If we didn't do that, the compiler would complain. This is not as nice as when there are only two arguments, but I've just shown it to you so you can still see that it is possible to use backticks with functions that have more than two arguments. Boolean logic is concerned with what is true and what is false. In Haskell, we have the bool type, which has only two valid values, true and false. There are a number of functions we can use to perform Boolean logic. The first type of Boolean function is testing for equality. There are two functions here. The first is two equal signs, which tests that whatever is to the left of it is equal to whatever is to the right of it. So if the two arguments are the same, it will return true, and if they are not, it will return false. The second is a / followed by the equal sign. This tests that the two arguments passed to it are not the same. So if the arguments are not the same, in other words they are not equal to each other, it will return true, and if they are equal to each other, it will return false. The reason for using this syntax is that it kind of resembles the not equal to symbol used in mathematics, which is an equal sign with a slash through it. Obviously the mathematical symbol is not readily available on keyboards, so it is much easier to define not equal like this. Let's take a look at some example code here. All of the variables C, D, E and F are of type bool. This means their underlying value will always be either true or false. For C, we are testing whether 2 is equal to 2. Obviously this is true, so the value of C will be the bool true. For D, we are testing that 3 is not equal to 3. 3 is obviously equal to 3, so the return result will be false. For E, we are testing that 2 is not equal to 3. This is obviously true. And lastly, for F, we are testing that 125 times 0 is equal to 0, which is true. The next type of Boolean function is for comparisons. The two values which are being compared must be orderable. So for G, we are testing whether 512 is less than 1024, which is true. For H, we are testing whether 1024 is less than or equal to 2, which is false. For I, we are testing that 256 is greater than 32.25, which is true. And for J, we are testing whether the string A is greater than or equal to B. Now in the alphabet, A comes before B, so A is considered to be less than B in terms of ordering. So testing whether A is greater than or equal to B results in false. These examples are shown using the comparison Boolean function on ints, doubles and strings. It is possible to do that because they all follow a well-known ordering. The next type of Boolean function is for combining Booleans. There are two functions for combining, logical AND and logical OR. The function for logical AND is two ampersands placed together, and the function for logical OR is two pipes placed together. Before we look at code, let's look at a truth table to better understand it. Suppose we have two variables x and y, which take the value either t or f, where they represent true or false respectively. So if x is true and y is true, then x and y will be true since they are both true. X or y will also be true since at least one of x or y is true. If x is true and y is false, x and y will be false because at least one of x or y is not true. X or y will be true, and so on for the rest of the combinations. Now let's look at some code using the combining functions. Here, k and l are bools. K combines two Boolean expressions using the double ampersand, which, like we said before, stands for logical AND. The first condition of 512 being less than 1024 is true, but the second condition of the character C being equal to the character D is not true, and so K is false. However, L has the same two conditions but is performing a logical OR. Since the first condition is true, the logical OR is true. The last type of Boolean function I want to cover is negation. This one is simple. Put in front of a Boolean, this will just turn it into the opposite. So if placed in front of true, it will turn it to false, and if placed in front of false, it will turn it into true. Now here is some code to test your understanding. This code is intentionally harder than the others. Let's go through it together. M is equal to not whatever is in the brackets. So we evaluate the brackets first. We have true, which by definition is true, and J, which is false. So true and J is false, and we are negating that by using the not function. So our result is true. N is equal to not false, which is true, and true. Since we are ANDing true with true, the result is true. O is equal to false, or not H, or not I. So we know H is false, and so not of H will negate false to true, and true back to false. And we know I is true, and if we not that, we get false. So this expression is false, or false, or false. And so the result will be that O is equal to false. That's it for Boolean logic. It can seem like quite a lot if you are new to it, but after a while of using it, you will get the hang of things. Suppose we want to write a function which takes in a list of ints and then returns a string describing the total number of items within that list. There are a few different ways in which we can write this function. Let's write an implementation of the function and call it description1. It takes in a list of int and returns a string. And here is the implementation. This is more complicated than anything we have seen before, so let's take it step by step. We are using the concatenation operators here, so it joins all of the strings together to produce one final string as the result. We use the length function, which is part of the prelude, to get the length of the list. The length is the number of items in the list. But the length returns an int, and we cannot concatenate a string with an int, so we need to convert the int to a string. And that is exactly what the show function does. It takes the int and converts it to a string. Then all of this is concatenated into a single string, and when we call the function, we get our result like so, as we would expect. Let's implement the same function, but this time using a where clause. Where clauses allow you to divide your function logic into smaller parts. Here is the alternative implementation. Let's go over what is happening here. We use the where keyword to introduce a new block for the function in which we can create bindings that we can then reference in our function body. These bindings are private to the function and cannot be accessed by other functions in your source code file. So in our case, we are creating two variable bindings. The I in length I is short for int, and the S in length S is short for string. Type signatures within the body of the where block are optional, but I have included them here for completeness. The first value, length I, is the result of calling the length function on the argument x. This is exactly the same as the length function being called in description1. The second variable, length s, is the value returned as a result of calling the show function. We pass in the value of length I here because we want it converted from an int to a string. This is again the same as what we did before in description1 by calling the show function. Then finally, in the actual function body, we refer to the variable length s to get our final string which we return, and when we call the function, it works in the exact same way as the previous one. Now this particular example is not too complicated, so it may make more sense to just leave the function definition without the where clause. But occasionally, you will need to define a function which can contain some quite complicated logic, and that's where where clauses can become useful. I've just used this trivial example to illustrate how you can define where clauses and use them within your functions. Before moving on, let's discuss some important points when it comes to writing where clauses and how it relates to whitespace. You always need to place the where keyword on a new line and indent it slightly more than the function name. The convention is that the where keyword should be indented 2 spaces here. If you do not indent the where keyword, you get a parse error indicating you need to fix the whitespace in your code. The body of the where clause needs to be indented slightly more than where the where keyword is indented to. So it is convention to indent the where keyword by 2 spaces and the where clause's body by 4 spaces. Each line in the where clause's body needs to be indented the exact same amount like it is shown in this example. If you do not follow these whitespace rules for indentation, you will get a parse error when you try to compile your code. Thankfully, these rules are quite intuitive and actually make a lot of sense. Just remember, put the where keyword on a new line indented by 2 spaces and the body of the where clause indented by 4 spaces. We will look at where clauses in more depth in a later module. For now, if you need to break up the logic in your function definitions, you can use where clauses as a convenient way of doing so. Another Haskell language feature which is similar to where clauses is known as let expressions. Let expressions allow you to create a new scope for bindings. It consists of 2 parts. Firstly, a list of declarations, and secondly, an expression in which the declarations are in scope and can be used. Let's make this concrete by looking at the same toy example as we did for where clauses. Here we have the same function, description1, which takes in a list of ints and returns a string describing how many items are in the list. Let's implement the same functionality using a let expression which breaks down the intermediate steps of calling the length and show functions. We begin the definition of the let expression by using the let keyword and defining a list of declarations, each separated by a new line. We then end the declarations with the in keyword and a final expression. The expression after the in keyword has access to all of the declarations which we made. We say that description2 equals the let expression. What does that mean exactly? It means it will equal whatever value is present in the expression found after the keyword in the let expression. So if we call the function just like before, the end result is the same. Within a let expression's bindings, you can put type signatures, function bindings, and variable bindings. It is also important to take whitespace into consideration. Technically, your code will compile as long as the lines for the let expression are indented at least 1 space further than the column containing the function declaration above it. But convention is to make the whole let expression aligned to the same column like we did so here. It is also easier for us to parse with our eyes when it is like this, and so indenting like this is what I would recommend. So you must be thinking, what exactly is the key difference between where clauses and let expressions? Although they are different in syntax, they basically do the same thing, right? They both introduce a private scope where you can declare bindings of functions and variables and use them. The immediate difference, that should be apparent to you, is that whereas for a let expression we declare the bindings first and then the expression afterwards, for a where block it is the other way around. Another important difference is that a where block is a syntactic construct, whereas a let expression is an expression itself. This means a let expression can be placed anywhere a normal expression goes, giving you quite a bit more flexibility when you want to introduce a private scope. So when exactly should we use a where clause or a let expression? A good reason would be to break up complex logic into smaller pieces to aid readability of your code. Rather than putting lots of function calls inline, you can use a where clause or let expression to break it down. Another reason would be to create a new scope to contain function definitions or variable definitions that you would like to remain private. When it comes to choosing which one to use, a let expression or a where clause, it is really just a question of style. Use whichever one you prefer. I personally prefer where clauses, unless I am in a place in the code where it is not possible to put a where clause, in which case I use a let expression instead. This is probably a fine guideline to follow as a beginner. As you become more comfortable, you can amend your style as you see fit. You can use if expressions in your code when you need to run your code based on some condition. If expressions take the form of if Boolean expression, then A, else B. So if the Boolean expression evaluates to true, then run the expression A, and otherwise run the expression B. Let's see some example code. This function takes in an int, and if it is odd, we return the string hello, and if it is even, we return the string bye-bye. So the type signature is defined that we take an int and return a string. And the body of the function is defined so that if the call to odd x returns true, then it returns hello, and otherwise it returns bye-bye. Odd is an inbuilt function which returns true if the number is odd. There are some things you should note about if expressions. You have to have all of it. If, then else. You can't just have an if without the corresponding else, like you can in other languages. There is no need to put a return statement, like you need to do in other languages. The value of the expression after then or else is returned automatically. Also, you don't need to put brackets after the if like in other languages. We rarely actually use if expressions in Haskell. Rather, we use pattern matching and guards, which we will cover in a later module. But for simple functions, it can make sense to use an if expression, like is shown here. Recursion occurs when something is defined in terms of itself. The factorial function is a common example which is used to show recursion. For those who don't know, it is defined as the product of all positive integers less than or equal to n, with 0 factorial equal to 1. We use the exclamation mark as notation for it. So for example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, which is 120. This is an example of the factorial function defined recursively in Haskell. For the situation where n is equal to 0, then by definition 0 factorial equals 1. Otherwise, the value is whatever n is currently multiplied by the result of calling factorial again with the argument of the number minus 1. Recursion is an extremely important topic in functional programming, and we will cover it in much more depth in a later section. For now, just understand the basics. And the basics are that there should always be a base case which ends the recursion. In this case, for us, that is when n equals 0. If there is no base case, you can end up in an infinite loop. Haskell code is organized into modules which export functionality, which can then be imported into other modules and scripts as they are needed. Let's consider a simple example to illustrate the basics of importing. Haskell defines a type known as int8, which can store any integer value between minus 128 to positive 127. However, this type will not be included in your script by default, and so if you want to use it, you need to import it. For our purposes, right now, we just need to know about the simple form of the import statement. We will look at different ways of importing, as well as Haskell modules, in more detail in a future section. Let's say we want to use the int8 type in our script. All we need to do is add an import declaration at the top of the script. This declaration tells Haskell we want to import the data.int module. Everything that the module exports will then be available to use. In our case, we just want to use the int8 type, which is one of the things exported by the module. Since we've imported it, we can then use the imported type within our script. Remember, it is important that the import declarations are placed at the top of the script. If you place the import declaration somewhere else in the file, after other things like function declarations, then you will get an error like so. That's pretty much it for now about simple imports. A function defines a mapping from a value of an input type to a value of a return type. The types are specified in the type signature. For example, the function signature for the factorial function we saw before takes an int and returns an int. This means that the function will accept any int value as input, and the return value can be any int as well. A partial function is a function which has no result for a valid value of the input type. There are a number of partial functions which are defined in the Prelude, many to do with operations on lists. For example, the head function takes in any list and returns the first item in that list. So the head of a list containing 1, 2, and 3 would be 1. The head of a list containing the two strings hello and goodbye would be hello. But what happens when we try to find the head of an empty list? Well, if you try to do that, it will blow up in your face. Your whole program will crash and it will say, exception, empty list. Why does it do that? It does that because head is a partial function. It is only defined for a partial number of possible inputs. And when it gets an input for which it is not defined, it throws an error and blows up. In this case, it is not defined properly for an input of an empty list, so this happens. Another partial function is the last function which gets the last item in the list. It suffers the same problem that for an empty list, it will blow up as well. This is because it is a partial function too. Most people argue that partial functions like these in the Prelude are a mistake, and instead use safe alternatives. We will look at some of these safe alternatives in later modules. In reality, there aren't that many partial functions in the Prelude, so it is not that much of a problem. And they serve as a useful teaching tool to teach students about partial functions anyway. For now, just remember that functions that you define should not be partial. That is, they should be defined so that they handle any input value of the input type. They should be total in their definitions. And that's the end of the module. We've covered quite a lot, and it is more or less fundamental information which you need to be aware of before we go any further. We began by discussing what Haskell actually is, as well as understanding that the Prelude module is automatically imported and available to us in our source code files. Then we moved on to examples to illustrate what we mean by purity, and we also discussed how to declare variable bindings and types, as well as some of Haskell's built-in types. We made a pit stop to illustrate how whitespace is important in Haskell and how strong type checking saves us from errors at runtime. We saw the different styles of comments that we can make in our Haskell files, and we even saw an example of a literate Haskell file where comments are the default. We then moved on to understanding functions, as well as how we can use backticks to turn prefix functions into infix ones, and we also explored Boolean logic, where clauses, let expressions, conditional if then else expressions, and simple examples of recursion and importing. We finally went on to discuss the differences between total and partial functions. Having covered all of these, you now have a good base on which to start learning more concepts in the next module of the course. See you there.